All right, let's take a look at our homework last night, page 495. We need to go over question number 2. It says a 65.2 kilogram student on a 2.5 kilogram skateboard moves at 0.40 meters per second to the west. He jumps off the skateboard with a velocity of 0.38 meters per second at 30 degrees south of west. What's the velocity of the skateboard immediately after he jumps? Let's draw a picture. Here's the skateboard. The skateboard initially includes the mass of the student, so we're going to say that its mass is 67.7 kilograms, and its velocity is 0.40 meters per second to the west. That's before anything happens, before the event, the interaction, the explosion, for lack of a better term, happens. The explosion or the event happens right here. The skateboarder goes down here. We're going to call the skateboarder object number 1. His mass is going to be given as 65.2 kilograms. His velocity is 0.40 meters per second. 0.38 meters per second at 30 degrees south of west. So there's our angle right there, south of west. It's measured from the west, and it's of course going south, so it's south from the west. We want to know what the velocity of the skateboard is immediately after he jumps. I'm going to guess the skateboard goes up this way. Okay, I may be wrong on that. I know that it's going to go up. It may go up and to the left. It may go up and to the right. We're not really sure about that. But it doesn't really matter if I've guessed wrong. Because in the end, I'm not using any numbers from object number 2 in my calculations. That's, in fact, what I'm trying to find. So we are going to say that the mass of the skateboard is 2.5 kilograms. We are going to say that we're looking for the speed, but that's all we really know about object number 2. Now, if you had me for Physics 20 last year, especially Physics 20 semester 2 last year, I really focused on this. I said, when we see a funny angle like 30 degrees, there's always a quick response to that we have. That response is always, I don't like funny angles. I don't like you, funny angle. Get away from me. Let's get rid of funny angles. We have a 30-degree angle right here. We don't want it. Let's get rid of it. Let's draw a little thing off to the side here. We got 30 degrees measured from the x-axis here. The hypotenuse is 0.38 meters per second. This is the x side of that triangle. This is the y side of that triangle. What I'm basically going to do here now is get rid of this 30-degree angle. I don't want it. I don't like it. I'm going to get rid of it and turn everything into an x-axis or a y-axis variable. Which side of the triangle is that x component? Opposite, adjacent, or hypotenuse? It's adjacent. So I'm looking for the adjacent side. I've got the hypotenuse. Which trig function am I going to use with adjacent and hypotenuse? Cosine, right. So let's say cosine 30 degrees is equal to x, that's the adjacent side, over the hypotenuse of 0.38 meters per second. X ends up being equal to 0.38 times cosine 30. 0.32908. 08. Hey, good enough. 5 digits is good there. Let's do the y component while we're at it. The y component is going to be the opposite side of the triangle, so it's going to be sine 30 degrees is equal to y over 0.38, and y ends up being equal to 0.19 meters per second. So what I've basically just done is replace this 0.38 meters per second with this, a y component of 0.19 and an x component of 0.32908. Now I don't have a funny angle. Now I'm going to actually go back to my original diagram, but I want you to understand that that's basically what I've just done. I've just taken away that funny angle and replaced it with a 0.329 x component and a 0.19 y component. Now let's do the x and y components of the entire thing. We know that pi is equal to pf for both x and y. And of course, there's one object before the collision, m1, v1, I. or sorry, MVI, I should say. Two objects afterwards, M1 V1F plus M2 V2F. Total mass before the collision is 67.7 kilograms. VI is negative 0.40 meters per second. Negative because it's to the left. 0.4, why is the entire thing 0.4? Put in for the x component here. It's all on the x-axis. How much of that 0.4 is on the y-axis? 0. So let's put all of it on the x. Good. M1 V1F. M1 is 65.2 kilograms. Tell me what V1F is. This is the part that's the turning point. You either get this question if you do this next step correct, or you don't get this question if you make a mistake on the next one. Okay, this is a turning point in this question. What is the value of V1F here? 0.32908, 0.33, right? It's actually negative, Jared, because it's to the left, right? Why is it not 0.38? Because that's y and x combined. I just spent the time separating y and x so that I could put the x component of the value of the x component of 0.38 with the x component when I go to analyze it. And then the y component when I go to analyze the y component. I don't want to go and put in 0.38. That's the combination. I don't want that. I don't like funny angles. And that 0.38 is at a funny angle. M2 is 2.5 kilograms. And then we solve for VF. Anybody got a value of VF there? Negative 2.249 meters per second for the x component. Let's do the y component now. Once again, we're going to say PI is equal to PF. Initial momentum MVI equals the final momentum M1 V1F plus M2 V2F. Tell me what VI is. How much of that 0.4 meters per second, that initial velocity in blue up there, is y component? 0. None of it's y component. So we're going to cross off that entire term, m times VI. 0 equals M1, 65.2 kilograms. It's the mass of the person, times V1F. Tell me what the value of V1F is here for the y component. How much of that 0.38 is y component, Dylan? Good, 0.19. I don't want to put in 0.38. I spent the time at the beginning of this problem getting rid of the 30 degrees. I don't want to speed at that 30-degree angle. I want to speed along the y-axis, which is 0.19 meters per second. It's going to be downward, though, right? It's going to be negative because it's downward. So we're going to make it negative 0.19. M2 is 2.5 kilograms, and then we turn around and solve for V2F. Anybody have a value of V2F there? Thank you. 4.9552 meters per second. Now we do the same thing as we've done a million times before in Physics 20 and in Physics 30. What do you do with this VF x component and this VF y component? Do a triangle. Here we've got negative 2.249, so that's 2.249 to the left. And we've got 4.9552 upwards. Solve for v using the Pythagorean theorem. Something's wrong with that. No, sorry, no. Looking at the wrong one. How do you find that angle is measured from the very start of the vector diagram? Opposite, adjacent, inverse, inverse tangent. Good. Of opposite over adjacent. We end up getting an angle of 66 degrees there. And it's going to be north of west because our angle is measured from the west. Right? It's measured with the x-axis or from the western axis there. Anybody get that question, just out of curiosity? No? Is anybody on the right track for that question last night? Okay, just kind of messed up on something. What'd you mess up on? Oh, so you did everything right. You just messed up on the math. Oh, that's too bad. It happens. Just don't do that on Thursday on your test, right? I think it's 18. I'll check that for you for tomorrow. Yeah, yeah. Okay, I'd like you to take about 90 seconds, guys, about a minute and a half, and do this question. Then we'll do it as a class, okay? See what you can do with it. It looks tough, but don't make it harder than it has to be. One of the things that I get from people after tests, sometimes this drives me crazy, sometimes it's a fair point. One of the things I get is the test questions aren't like the book questions. The test questions aren't like the homework questions. Here's the thing. They are and they're not. The test questions are like the book questions, and they're not like the book questions. We have to be able to recognize that the test questions are in context, and they sometimes seem harder because they're in a context that you've never seen before. But it's exactly the same concepts as we've done a million times before in class. That's what you've got to see. Strip away all the stuff that makes it seem harder and turn it into something we've done in class. Here's a good example of a question that, if you saw this on a test, would seem tough. Okay, let's do it right now and work through it and show you that, hey, look, it's not really that hard. We can work through something like that if we see it on a test, okay? So about a minute and a half, and then we'll go over it as a class. Let's take a look at this one here now, okay? Let's draw the picture. It's kind of there in front of me already, but let's make the picture a little bit nicer here. We've got this hopper car going to the right with a velocity of 2 meters per second. It's already written down. Its mass is 1.00 times 10 to the 4 kilograms. We'll call that object number 1. Object number 2, that's going to be the coal. That's coming downward. We don't know what velocity it's coming down at, but we do know its mass is 1.20 times 10 to the 4 kilograms. Now, the collision is going to take place right here. This coal hits the hopper car. Where is this hopper car / coal combination going to go after this collision takes place? Where should it go? Theoretically, where should it go? To the right and down. Down and to the right. If you've got a momentum to the right and a momentum down before the collision, then you have to have a momentum to the right and a momentum down after the collision. Does that make sense? Here's the thing. It does go down a little bit, but it goes down so little that the y component isn't going to matter. Can anybody explain to me why it goes down so little? Why is the y component effectively irrelevant? Michael? It's on the track, and it can't go down because the track is on the earth, right? So when it goes down, it has to take the earth with it. Well, if you give it a certain amount of momentum downward, and the earth is moving with it, and the earth has a mass of 10 to the 24 kilograms, how fast is it going to be moving downward with the earth? Like basically none, right? 0.0000000, whatever, meters per second. So it's basically got no y component. Intuitively, we know that, right? Intuitively, we know that when you drop coal in a hopper car, which way is the hopper car going to go? This way. The reality is there is a tiny bit of a y component, but we're not even going to touch it because it's so small that it just doesn't matter. We know that it's so small that it just doesn't matter because that momentum gets transferred to the earth, and the earth just isn't going to move any measurable amount. I can't think of one. No, can't think of one. Justina's question was, will there ever be a problem in which the x component doesn't matter? There's times when you only have to do the y component because maybe you solve for whatever you need to solve for right away and you're done. You don't need to touch the x component because you just got the answer already. But I can't think of a situation where the x component wouldn't matter. Yeah, unless you're pushing up against, maybe against a giant building or something like that horizontally, which isn't really going to move either. Basically, whenever you got a problem like this, where something is going down towards the Earth, the y component isn't going to matter. Does that make sense? There's a question on your assignment that's similar to this, actually. You guys know which one I'm talking about? Which one am I talking about? No, I think it's question number 6, I think it is. Yeah, there's a picture. There's a cannonball. Yeah. The cannonball, right? The cannonball is fired upward like this. What happens to the little cart that it's on? Well, it goes backwards this way, right? So what do we know about the y component? Well, technically, this thing gets pushed this way. But how much downward does it get pushed? Effectively nothing, because the Earth goes with it. So you're only going to analyze the x component for that one as well. When it's being pushed down against the Earth, ignore the y component. It's there, but it's so small that it's just not going to matter. Okay, let's do this now. Let's analyze just the x component. We're going to say pi is equal to pf. We're going to say m1 v1i plus m2 v2i equals mvf. m1 is 1 times 10 to the 4. v1i is 2 meters per second. This is 0 because the coal is, although it's moving vertically, it's not moving horizontally before the collision takes place. The combined mass is 2.2 times 10 to the 4. And we solve for VF. VF works out to be 0.909 meters per second. Now, normally I'd say that's not my final answer. That's only my x component. But because since the final answer has only an x component, it is the final answer. Okay, does that make sense? How many people got that? Good. All right, I want to do one more example with you here today, okay? Then we'll give you a chance to work on a couple questions. This one says a 19.6 kilogram curling stone. Anybody curl here? Is anybody a curler? I've curled a couple of times. Yeah, they're 20 kilograms. They're almost 50 pounds. They're heavy. They're very, very heavy. And curling is very difficult. It looks so easy, but it's so hard. I've done it 2 or 3 times, and I'm terrible at it. Absolutely terrible. You know what the hardest thing about it actually is? You know what the hardest thing I have is? Sweeping. It's like somebody throws a rock and you're trying to sweep it, and it's like I can't even stand up on the ice, let alone keep up with a moving rock and sweep all at the same time. Watching women's curling on TV is the most annoying thing. I think, isn't men's curling kind of right up there with it? Isn't men's curling kind of right up there with it?
I don't know, I was just trying to get more questions.
I don't actually mind every once in a while watching it on TV. It's not something I want to watch every weekend, but. Don't watch it then. All right, so we got a curling rock that's almost 50 pounds. Moving at 1.2 meters per second to the north, strikes another curling rock that's stationary. And the first one, it says it moves off with a velocity of 1.17 at 12 degrees east of north. So it's going to move off up here. Where do you think object number 2 or rock number 2 is going to go? It's a glancing collision, right? Rock number 1 hits rock number 2. If it hits it straight on, rock number 2 is going to go straight. But if it hits it kind of on the side, then rock number 2 might go one way, rock number 1 is going to go the other way. If rock number 1 goes to the right and up, rock number 2 is going to go to the left and up. You know what, though? If we messed up on that guess, that's okay. Because that's not the important one. The important one is the red one, the red diagram here, and the blue diagram. That's the givens. The green one is just our prediction as to what our answer is going to be, basically. What do you say to yourself when you see that blue angle there, that blue vector, 1.17 meters per second at 12 degrees? Let's get rid of the angle. We don't like you, funny angle. Let's get rid of you. Let's draw it off to the side and get rid of it. We get 12 degrees here with the y-axis. This is 1.17 meters per second. This is x. This is y. Which side of our triangle is the x-axis here? Is it opposite, adjacent, or hypotenuse? Yes, the x-axis. Good. It's the opposite side. So we're looking for opposite right away. We have the hypotenuse. Which trig function goes with opposite and hypotenuse? You guys know this. Sine. Sine 12 degrees is equal to opposite, x, over hypotenuse, 1.17. So x ends up being equal to 1.17 times sine 12 degrees. What is that? 1.17 times sine 12 degrees. Make sure you're in degree mode. 0.243. 0.257? Okay. 0.243257. Thank you. The the y side is going to be found by the cosine function because it's the adjacent side. So cosine 12 is equal to y over 1.17. Tell me, please, what 1.17 times cosine 12 is. Okay, that's good enough. 4 decimal places is good enough here. So what have I just done with my little aside over here? I've just replaced that vector, 1.17 meters per second at 12 degrees, with this, an x and a y. The x being 0.24 and the y being 1.14. Now I can go and do my thing. The thing that I've done many, many times over the last couple of weeks. Pi is equal to Pf. We're going to do it in the context of x and y components. M1v1i plus M2v2i, M1v1f plus M2v2f. This is something that happens, I would say, fairly often, although not always, on tests. When you get a multiple choice question that is a two-dimensional collision or two-dimensional explosion, we will find oftentimes that the mass is the same. What can I do if the mass is the same? Cancel. They do that sometimes because it's a lot of work. If we're talking about a multiple choice question, a two-dimensional interaction is a lot of work. They're giving us a bit of a shortcut. Cancel with the masses just saves you, 30 seconds plugging into your calculator. Okay, they don't always do that, but they often do that for us. Tell me what V1I is for the x component. Tell me what V1I is for x component. How much of that 1.2 meters per second is this way? None. Object number 2 is at rest, so obviously none of it's going to be x component. Total initial momentum, x component, horizontal axis is 0. V1F. Here's the deciding factor on whether you get this right or not. What's V1F? 1.17, 0.24, or 1.14? How much of that blue vector is on the x-axis, Dylan? 0.243. How many people agree with that? How many people see that? Okay. We're going to solve for V2F here now. It's an easy one to solve for. V2F ends up being equal to negative 0.243 0.257 meters per second. Then we do the y component. For the y component, again, we say pi is equal to pf. Masses cancel again. These curling rocks better be the same mass. It's hardly a fair game if they're not. V1I? Tell me what V1I is for the y component. Jared? 1.2. It's not 0 anymore. It's 1.2 because we're dealing with the y component. This one's 0 because it's at rest. Tell me what V1F is. Anybody? Just say it out. How much of that 1.17 is on the y-axis? 1.14. Right? We just found the y and x components of it. The y component is 1.14. Let's solve for V2F. I believe it works out to be 0.0555. .24 to the left. .0555 up. This is V, and this is theta. How do you get V? Pythagorean theorem, good. How do you get theta? There we go. What's different about this question versus the questions that we've done yesterday and just before the break? I'll tell you what's different about it. This. That's the only thing different about it, is that 12 degree, that funny angle, that thing that we don't like, that thing that we want to get rid of. What's different about the solution? This blue part that's boxed off over here on the right-hand side. How is this different than what we've been doing? It isn't. We just have to get this value and this value from over here. That's it. Don't remember this question. Don't memorize this question. Understand why we did what we did on the right-hand side there. Understand why we got rid of that funny angle, 12 degrees, and turned it into two other vectors, 0.24 and 1.14 meters per second. If you understand why that's the case, you will get every single one of these questions that get thrown at you. Okay? Try to memorize it. You'll get some of them, but not all of them. Does that make sense? Okay, here's what I'd like you to do. You guys have a little bit of a break over the other classes. You got a little bit more time to work on this today than the other classes did. I want you to work on two problems that go along with this, page 491. We are effectively done the unit. We'll check over these questions tomorrow. Tomorrow we'll also take a look at elastic and inelastic collisions. We'll revisit that in this context, but it's nothing new. It's just revisiting the concept that we've already done in another context. And we'll spend some time doing some reviews, so come with some questions.
Are these ones for homework?
Yes. Yes, they are for homework. If you They are for homework if you don't have them done in class here. What was the answer to the last one? I don't know. Never actually found the answer. Did anybody have the answer for that? For this last question, did anybody calculate it? 0.25 for the speed. And the angle was pretty small, I think. Justine, question? The angle is going to be pretty small, right? Because we're dealing with something right here that's a pretty small number. Did you get an answer, Justina? Okay, let's calculate it then, okay? That would be 13 degrees north of west. Okay? All right. Let's take a look at these two again. You got your assignment due tomorrow as well, but hopefully you're pretty much done your assignment. And then these two questions. So hopefully you're done that assignment or pretty close to it. And then hopefully you can finish these two questions in class here today.